So يا شباب last time we stopped at this point. We talk about the reversible. Last time we talked about the reversible work, and we said the reversible work for open system. The work for open system is unlike the case of closed system. The work for open system is equal to integration of VDV, not BDV. Okay. So last time also we have applied this actually to calculate the reversible work for some steady flow devices, and we have calculated actually applied this and calculated the reversible work in case when we have a compressor. So in this case the work will equal to integration of VDV. I mean, we said in case of incompressible substance, the volume, the density will be constant, or the specific volume will be constant. Then I can work of incompressible substance, like the case when we have a pump, will equal to the specific volume multiplied by delta B in this case. And I give you example last time to see what is the difference between actually compressing liquids and compressing gases, the input power required in this case. And we give this example. We said if we have steam and we work to compress this steam to the same pressure from 100 kilopascal to 1 megapascal, said if this actually is in the liquid form, liquid water, and I use the pump, then in this case the work will equal to about 1 kilojoule per kilogram in this case. But if actually this steam, the same amount of steam is in the vapor form or the gaseous form, in this case instead of pump I will be using a compressor in this case to compress the gas. And we have seen in this case the work required to compress the same amount of gas between the same pressure limit is equal to about 500 times in case actually when this substance is in the liquid form. And this gives us indication, Shabab, that actually gases, because of its actually huge volume, it requires actually more work to be compressed in this case in comparison to the liquid. And whenever we have an open system, we can generalize the case that the work will equal to integration of VDV. Okay, whenever the system is open system. In case of closed system, the work is equal to integration of BDV, not VDV. Okay, as we have learned in chapter 4. But if we have a reversible system, that means actually reversible means that we don't have any kind of losses of this system. So if this system actually is a kind of turbine, that means actually this turbine is producing the maximum work because we don't have any kind of losses in this case. So what about if this device is work-consuming device like compressor? So compressor is consuming work. We have electric motor. Usually it is running a shaft, and this shaft actually is driving the blades of the compressor so that it can take the gases and compress it actually to a higher pressure in this case. So the input power to the compressor is a mechanical shaft power. It consumes work in this case. But if this compressor is reversible, so in this case, the input work will be minimum or will be maximum. In case of turbine, Shabab, if we have a reversible turbine, that means we don't have any losses. So the work out of a turbine will be maximum in this case. Now what about the case of compressor? It is consuming work, not actually producing work. So the work in this case, if we have a reversible process, will be maximum or minimum?
Minimum.
Will be the minimum in this case. So if you have a reversible device, if this device actually is producing work, the work will be maximum. If the device is consuming work, that means actually the input work will be minimum in this case. But how can I show you, and this is something related to the mathematics, how if we have a system, a reversible system, let's say we have a reversible open system, how we can prove actually that this system, if it is reversible, it will be producing the maximum work when compared actually to the case of the actual system, in case when we have losses. So I want to just prove that the reversible work is greater than the actual work. Is it? By logic? It should be. We should have the reversible work if we don't have any kind of losses. The work out of this system in this case should be the maximum in this case, and it should be greater than the actual work in case when we have losses within this system. But to prove this mathematically, let's apply the first law equation for this open system. Then we can say for the reversible system, then we can say delta Q reversible minus delta work reversible. Q minus work will equal to the change of enthalpy plus the change in kinetic energy plus the change in the potential energy. This is for the reversible system. For the actual system, we can say delta Q actual, the first law of thermodynamics, minus delta work actual for the actual case system, in case when we have losses, will equal to delta H plus a change in kinetic plus a change actually in the potential energy. So if we have a process that change a reversible process and the actual process of the same system, it changes in enthalpy, it changes in kinetic energy and the potential energy. Enthalpy is a property. So does it matter actually is the process reversible or irreversible? So if you look at the TD diagram or PV diagram, we have a system undergo change from initial state to a final state 2. If this process is reversible, then delta H will equal to what, H2 minus H1. But if I followed another path here, another process through actually an irreversible process, and I reach also point number 2, so delta H in this case will also be what? H2 minus H1, because this is a property. It does not depend on the path followed. Just what we need actually is the final value minus the initial value. So actually this term, this right-hand side term, will be the same for both cases. Either the process is reversible or actually this process is actual process. And in this case, we can say delta Q reversible minus delta work reversible will be the same as delta Q actual minus delta work actual. So this term should equal to actually this term in this case, because the right-hand side will be the same in this case. Or we can say actually delta work reversible minus delta work actual, that should equal to delta Q reversible minus delta Q actual. Is it, Shabab? Is it?
Yes, yes.
So we can say delta is the difference between the reversible work and the actual work will equal to the difference between the reversible heat transfer minus the actual heat transfer. But by definition, if you remember, you call this for the definition of the entropy, we say delta S is equal to delta Q over T for the reversible process by the condition that this process is reversible. And we said in case of irreversible process, delta S will be greater than or equal to delta Q over T. This is for the case of irreversible process. It is equal in case of reversible, but in case of irreversible, it should be greater than delta Q over T. Why it should be greater than delta Q over T? Because due to irreversibilities, we should have actually some entropy is generated. Okay, so in case of irreversible process, like what we have proved based on the Clausius inequality and the definition of the entropy in the first class in this chapter, we said delta S by definition is equal to delta Q over T for the reversible process. And for the actual process or irreversible process, delta S should be greater than delta Q over T, because we have to have some irreversibilities in this case in terms of entropy generation. Okay, Shabab? But that means from this equation, delta Q reversible will equal to what? TdS. So I can just substitute here. This one will be equal to TdS. Just to divide the whole equation by T. So this TdS divided by T will be delta S, and here it will be delta Q over T, and here we can just divide by T. Okay. Now we have this term is equal to what? Delta S minus delta Q over T. So we said, based on the second law for irreversible process, delta S should be greater than delta Q over T. The difference between delta S minus delta Q over T should be, in this case, positive or negative? Should be what? Should be a positive value, because delta S is greater than what, Shabab? Delta Q over T in case of the actual or irreversible process. And that means the whole right-hand side term should be a positive value. By positive value, it is equal to delta Q, delta work reversible minus delta work actual divided by T. If this term is positive, that means this term is positive as well. And this term cannot be positive unless we have the reversible work is greater than what? Is greater than the actual work. Is it clear, Shabab?
Yes.
So, Yani, this is something just for your knowledge. We by default, if we have a system undergo reversible process, we don't have any losses. That means the system will be producing the maximum work because we don't have any kind of losses. But this is Yani the mathematical proof. If you want to look, okay. If we have a compressor, if we are designing a compressor is consuming work. So we need this work actually provided to the compressor is usually through an electric motor, and this electric motor takes the electrical power and generates shaft power. Then it can drive the impeller of this compressor. So as the input work to the compressor increase, that means actually more electrical power will be consumed in this case. So if I'm designing a compressor, so I should design it for what? Minimum work input or maximum work input?
Minimum.
Minimum work input. So in this case, minimizing, in this actually today, we'll be actually learning how to minimize the compressor work. So minimizing compressor work, okay? But if we want to calculate actually or design actually a compressor for minimum work, in this case, we have defined actually that the reversible work, in case we don't have losses, isentropic process, is equal to the work is equal to integration of VdV plus kinetic plus potential energy, which we can neglect in this case. But the work as the compressor is open system equal to integration of VdV. Let's represent this process on the PV diagram. In case of compressor, usually the fluid is coming at pressure B1 and it is leaving actually at higher pressure B2. So fluid, let's say we have a compressor is compressing air from state 1, then it will be compressed in the compressor until the higher pressure B2. What about the volume, Shabab? When we compress something, so that means the volume is what? Reduced or increased?
Reduced.
It will be reduced in this case. So that means while increasing the pressure inside this compressor from state 1 to state 2, in this case the specific volume or the volume actually of the gas will be reduced in this case. Type the area, Shabab, that is representing the work on the PV diagram. Which area in this case? Keep in mind it is VdV, not BdV.
On the pressure axis, y-axis.
In the y-axis, exactly. Because if it is closed system, we can say the area under the curve will be the area on the PV diagram. It will be actually this area, the area under this curve. But this system is not closed. And the work in this case is not equal to BdV. The work is equal to VdV. That means actually the work can be presented by the area on the VV diagram, not BV diagram. So it will be actually the projected area in the vertical direction. So this area is representing actually the work done by the system in this case. So the area for the open system is represented actually on the VB diagram, not BV diagram. So this should be represented actually the work done by this compressor. But let's see, first of all, if we have an isentropic compression process. So for isentropic process. In case of isentropic process, we have the relation PV. We have proved this relation in case when we have an ideal gas undergo an isentropic process. So we have the relation PV to the power K is constant, and we have defined the K, which is the specific heat ratio of this gas CV divided by CV in this case. So PV to the power K is constant in case when we have an isentropic process. That means if this compressor from state 1 to state 2, we can say V1 to the power K is equal to V2 to the power K, and it is equal to constant. We can call it as C. So the constant is equal to V1 to the power K. It is the same as V2 to the power K. But from this relationship, how we can get the volume as function of pressure, so that we can substitute in this relation and do the integration to calculate the work of the compressor in this case. So based on this relation, VV to the power K is constant, we can say V will equal to the constant divided by P to the power 1 over K. Okay? Just take this relation and take it here and substitute here and do the integration. Then we can calculate the compressor input work in case if the process actually is isentropic compression process from the initial state to the final state. But let's do this integration. So the work reversible for the compressor will equal to integration of V, which is C divided by B to the power 1 over B, integration of delta B from the pressure B1 up to the pressure B2. We can take C to the power 1 over K outside. It will be B to the power, it is down there, so it will be B to the power minus 1 over K. Do the integration, it will be B2 to the power minus 1 over k plus 1 minus b1 to the power minus 1 over k plus 1 divided by minus 1 over k plus 1. Is it, Ishaba? Is it done this way?
Yes.
So do this integration. This constant is constant to the power 1 over k. Type here is the constant. C is equal to b1 v1 to the power k, b2 v2 to the power k. I need this constant to the power 1 over k to substitute here. It is constant to the power 1 over k. That means it will equal to b1 to the power 1 over k multiplied by v1 to the power 1 over k. It will be actually 1 in this case. So the constant to the power 1 over k will equal to b1 to the power 1 over k v1, and also it is the same as b2 to the power 1 over k multiplied by v2, because v2 to the power k multiplied by power 1 over k, so it will be v2 in this case. Just take this constant as b2 to the power 1 over k multiplied by v2 and substitute here in this term, and take it as b1 v1 to the power 1 over k multiplied by v1 and multiply it actually by the second term here. Then if you do that, you will find the reversible work will equal to b2 multiplied by v2, because it is b2 to the power minus 1 over k plus 1 multiplied by b2 to the power 1 over k. So we will be left actually with this one, which is b2 to the power 1. Like this, it will be v2 in this case. So b2 v2 minus b1 v1 divided by this term. It can be actually built as actually 1. It will be k minus 1, and here we have the parameter k. So in this case, the work for an isentropic process will equal to k, which is the specific heat ratio, k divided by k minus 1 multiplied by b2 v2 minus b1 v2 b1 in this case. But in case of ideal gas, we have bv is equal to what? bv is equal to what,
Multi.
Is equal to RT exactly. So we can just replace this term BV by RT. So in this case, we can say the compressor work, the reversible work based on the isentropic process will equal to K divided by K minus 1. BV is equal to RT. So it will equal to RT2 minus RT1. We can take it R as common, and we can take T1 as common. So it will be here T2 over T1 minus 1 in this case. But in case of isentropic processes, if you recall, we said T2 over T1 will equal to what? So this is K R T1 over K minus 1. T2 over T1 is equal to B2 over B1 for an isentropic process to the power K minus 1 over K, and we have here minus 1. And this is the case, the compressor work, if this process actually is an isentropic compression process inside this compressor. Type isentropic compression means what? This line is following BV to the power K constant. The process is isentropic. Type isentropic process means what? The process is reversible, and the process is also what? Is also adiabatic. Reversible, we don't have loss, and the adiabatic means what? We don't have what? We don't have heat transfer in this case. We don't have heat transfer. So this is in case when we have isentropic process, compression process, we can calculate the compressor work. This proof, ya shabab, is not there in the slide. You'll find this equation is there, but we have learned how to develop it. So this is the compressor work in case when we have isentropic process. And the isentropic process, we have BV to the power K is constant, and the process is reversible. We don't have losses, and it is adiabatic. We don't have heat transfer. Type, how we can further reduce actually this compressor work? Is there a possibility, Shabab, to reduce this compressor work? What should we do? Can we do something, kind of cooling or something?
There is no friction and no heat transfer, so we can't do anything.
So, but how we can further do it? This is the case of we have isentropic process, and this work under the VB diagram, this is the work. Can we reduce this work a little bit further by doing something else? So we said for the isentropic process, this process is what يا شباب؟ adiabatic. So we don't have what? Do we have heat transfer? So this process is adiabatic. But what will happen when you compress the gas and we don't have any kind of heat losses? This is the compressor here. And these are the blades here. The flow is coming here in the axial direction, and it is leaving in the radial direction between the blades. It's collected here and going out. Okay? Right. Compressing the gas, that means I'm raising the pressure. So what will happen to the temperature? Temperature will be what? Will be raised. Is it, Shabab?
Yes.
طيب, if I am actually, I want to reduce the final volume. If I am able actually to reduce the final exit volume of the gases, then in this case, the area under this curve will be reduced. That means the compressor input work will be reduced in this case. But while raising the pressure, the temperature will be raised in this case. That means if I am able actually to reduce the final temperature, if the temperature is reduced a little bit at exit section, that means actually the volume will be what? The volume also of the gas will be what? Will be contracted a little bit. So if I am able to cool down the gases while the compression process, then in this case I can reduce the final what? I can reduce the final volume. If I am able to reduce the final volume here, that means actually in this case the area under the curve will be reduced. And the volume anyway, if the volume of the substance is reduced, that means the work input should be reduced. And we have learned this when we compare the case of liquid. You see here, compare the case of gas, we need 500 times because of the volume. So if you are able to reduce the volume of the gas, that means actually in this case you are reducing the reversible or the input work to the compressor in this case. But how we can reduce the final temperature here? Here for the process, which is isentropic process, even we don't have any losses, but the process is adiabatic. So when you raise the pressure, the temperature will be raised. And in this case, the gases are not losing any kind of heat. That means the final volume will be a little bit high. But what happens? This is in case if this compressor is adiabatic, we don't have any kind of heat loss. But if I allow this compressor to exchange heat actually with the surrounding, that means it will lose some heat to the surrounding. That means the final temperature will be what, ya shabab? For the same pressure, final temperature will be reduced, and the final volume will be what? Decreased. And in this case, the work for the compressor will be reduced in this case. So similarly to the isentropic process, we have this process in which we have heat transfer. We call it actually the polytropic process. In case of polytropic process, we have the same relation, but instead of K, we have the polytropic index N. BV to the power N is constant. And as I told you last time, the difference between polytropic and isentropic, it is adiabatic. Polytropic, it is not adiabatic. Okay? So that means the gases are allowed to exchange heat, the final temperature will be reduced, the final volume will be reduced. That means in case if we have a compressor undergo a polytropic process, BV to the power N is constant. N in this case, is not equal to K. It should be greater than 0. This value is just greater than 0. And it is greater than 1 for sure. Okay, it is around 1. But it is not equal to K. And the K is equal to what? CB over CB. Because if N is equal to K, this K actually, that means in this case the process is isentropic and we don't have heat transfer. Okay? So if we have a compressor, so second state, if we have polytropic process and compressor undergo a polytropic process based on the relation BV, and instead of K, we have N in this case BV to the power N is equal to constant. And we have seen here for the polytropic process, we can reduce the input work to the compressor. But what is the difference, Shabab? It is similar to the isentropic, but instead of K, I will replace it by N. Then in this case, the compressor work, the work input to the compressor, instead of K, it will be N. It is N over N minus 1 RT1 multiplied by B2 over B1 to the power n minus 1 over n minus 1. It is just the same relation I have developed for the isentropic process, but instead of K, I have just replaced K with N. N is called as the polytropic index in this case. And this work, in case of polytropic process, is less than the work in case when we have isentropic process. But can we do further modification? Can we reduce this input work a little bit further? Saleh, do you have an idea? Saleh, is the mic working? Oh, it seems there is a problem. طيب أحمد.
ما يشتغل المايك حق ثانية.
So Ahmed, do you have something? Do you have an idea how we can reduce?
لا والله.
So here in this case, شباب, we said for the polytropic process, we allow the system to exchange heat. So the final temperature is reduced, but still the final temperature is much greater than the end temperature. So T final, which is T2, is much greater than the temperature T1. Okay? It is increased, but compared to the isentropic, it is less than. The final temperature is less than the isentropic. But what if, if we are able to compress the gas without any temperature rise? The temperature will be the same as T1. So in this case, the process is what? Isothermal. Temperature is fixing, and we are raising the pressure. That means actually we have to cool down, or we have to have water jacket around actually this compressor. Then we can raise the pressure, but actually the temperature will try to raise when we increase the pressure. Temperature will be raised, but actually I will be cooling down this compressor actually using a water jacket or something. So the temperature will be fixed. That means the final temperature will equal to the initial temperature. That means actually in this case the final temperature will be the minimum in this case. So that should be the final. This is line. This is the line representing the case when we have the process is actually is isothermal. Temperature is equal to constant. Okay. Temperature constant, we have BV is equal to RT. Temperature is constant and the R is constant. That means in this case for this process, BV is equal to constant in this case because the temperature is constant. If the temperature is constant, we don't have temperature rise. That means the final temperature is minimum. Temperature is minimum, that means the volume of the gas will be the minimum in this case. And in this case, the gas can be compressed here actually to the final state. Let's say this is 2' and this is 2'. And this process, shabab, is the isothermal process. So if the process is isothermal, that means we are cooling down the gases while the compression process, so that we can have the final temperature is the same as the initial temperature. We don't have temperature rise. That means the volume of the gas will be kept minimum at the output of this compressor. And in this case, the work under this curve for the isothermal case will be the minimum in this case. So the third case, if we have isothermal process, the temperature is constant. Temperature is constant, we have BV is equal to RT. Pressure specific volume equal to RT. T is constant and R is the gas constant. So that means the pressure multiplied by the volume is constant. And in this case, the reversible work will equal to integration of VdV. Please, shabab, we have defined earlier the work for, if you remember, for a piston cylinder device, the boundary work was defined as what? Integration of BdV. And we have considered the same cases. We have considered the polytropic process, isentropic process, and we have generated the equation. Okay, but for the polytropic process, for a boundary work for a gas in a piston cylinder device, the boundary work was equal to what, shabab? B2 V2 minus B1 V1 divided by 1 minus N. This is for the polytropic process. But here we are talking about a compressor, open system. So the work is integration of VdV, not BdV. And the equation we have developed for the compressor work is N over N minus 1 multiplied by B2 V2 minus B1 V1. So here there is a difference. Okay, This is for the compressor. Following polytropic process, integration of VdV, we got this relation for the polytropic process, n over n minus 1, B2, V2 minus B1, V1. But in case of boundary work, when we have a gas in a piston cylinder device in chapter 4, we have developed the case if the process is polytropic. Boundary work will equal to B2, V1, B2, V2 minus B1, V1 divided by 1 minus n. Okay, Shabab, this is something I have to tell you, because if it comes to your exam and I ask you the polytropic process for a compressor, and then you just go and take it for the boundary work. Okay, this equation is totally different. This is a closed system. This is an open system. Okay, Shabab?
Okay.
So just to keep it in mind, I will just remove it. Type in case of isothermal process, I'm not talking about the exam, I'm just telling you something that may just be, you may be confused with. So integration of VdV, V will equal to C over B. So it will equal to integration of C over B dV from B1 to B2. So it will equal to constant. That constant is BV, and BV is the same as RT. Multiplied by the integration of delta B over B, which is lim B2 over lim B2 over B1. And this, Shabab, should be the minimum input work to the compressor in case if the process is isothermal. But can we make the process isothermal, Shabab? In reality, we have a compressor like this. We have blades here. While the flow is going through the blade, area is increased in the direction of the flow, so the pressure will be raised and the temperature will also be raised. That means if I'm using external water jacket here, it will do nothing. It will reduce the final temperature a little bit, but in this case I have to apply a cooling system around each blade. So that actually when the flow is going, pressure will be raised, temperature will try to raise, I will have a cooling system for each blade. But is it possible to have a cooling system around each blade, which is rotating actually with very high RPM? This shaft is rotating, okay? 3000 RPM or something. Can we do that?
No, it's hard.
So it's too hard to do it. So we cannot reach this stage to have isothermal compression. Because usually when you compress, raise the pressure, the temperature directly will be raised. We cannot keep it constant. So is there a solution, Shabab? What do you think? Is there a solution between, we said polytropic, we can do it. Polytropic can be done, which is in between. Isentropic is the maximum work input. Polytropic, it will allow heat transfer. So we can reduce the final temperature at state 2 prime. At the third state, when it is isothermal, we said we cannot make it isothermal, but we can make it polytropic. But is there a solution with this polytropic process to minimize the compressor work? So there is. We can do something. We can divide the compressor. So instead of using one compressor, we can use more than one compressor. So instead of compressing directly from B1 to the final pressure B2, we can compress the process in one compressor from B1 to intermediate pressure, let's say Bx. And then we can use another compressor to compress from this intermediate pressure Bx to B2. And this is compressor 1, and this is compressor 2. And in between, the gas that is leaving here, we can take it out here and make intercooling. We can have some cooling water. Then this gas will be cooled to the initial temperature. So let's say the initial temperature is T1, and here actually is the temperature T2. Then in this case, we can cool down the gas. The temperature T2 is high. So this coming here at T2, we can cool it actually to temperature T3, which is the same as the initial temperature. So in the second stage, we cooled it down using cooling water to the initial temperature. So we get back the gas to the initial temperature. Then I can compress in the second compressor. The process here is polytropic, BV to the power n is constant, and in the second compressor, is polytropic. BV to the power n is constant. But in between, we have here, we have cooling water. We have cooling systems. The gas leaves the first compressor, first stage. I take it and cool it down to the initial temperature, and then I can continue the compressing process. But let's look at this on the PV diagram. This is the PV diagram. This is the pressure B1, and this is the pressure B2. Okay? Here what we said is what? Polytropic is the best that we can do. This is the polytropic process. From state 1 to state 2. BV to the power n is equal to constant in this case. But we said we need to just reduce it a little bit. So we said we can do something. We can just compress in two stages. To an intermediate pressure Bx. So I will be compressing from state 1 to state 2 at the pressure Bx. Then I will cool down the gases from state 2 to state 3 in the intercooler. We call it intercooler because we have some cooling water will be cooling down the gases, leaving the first stage of the compression at constant pressure from 2 to 3. Then I will be using another compressor from state 3 until we reach state 4. This process as well is a polytropic process. BV to the power n is constant. So the area under the curve in this case will be what? Will be the area under the green line, which is this area. This is for the two stages. If I'm using only one stage directly from 1 to 2, that will be the representation. And this is the line I'm just drawing. This is the line, the blue line. So the area under the curve will be what? The whole area, this whole area. So that means if I'm using staging, that means actually I am saving this area from the compressor work. So this is the work saved. Do you understand this, Shabab?
Yes, but Doctor, if we reduce the temperature like the first one, aren't we doing the same process again? No difference.
Reducing the process from 2 to 3?
Yes.
Yes, in this case, we have just to take the gases leaving the first compressor, cool it down using cooling water outside the compressor. And then take it to the second compressor, second stage of compression. Then it will be compressing from 3 to 4. So from 1 to 2 to 3 to 4, the work will be presented by the area under this curve. Compared to the case directly from 1 to 2, then actually I have saved this area. This area has been saved from the compressor work using multi-stage compression with intercooling. So in case, let's make it a little bit clear. So the fourth solution, we said the minimum is the isothermal, but we cannot do it. So we can do something in between, which is actually multi-stage compression, not only one stage, with intercooling. Cooling in between, intercooling. So in this case, we have this is compressor 1. Let's say air is coming here at state number 1, and it is leaving at state number 2. T2 is greater than T1. I will just pass this air inside an intercooler. We have here cooling water is passed to reduce the temperature. So in this case, the air will be leaving here at temperature T3. We call it for complete intercooling. Complete intercooling, that means T3 is the same as T1. We call it complete intercooling. Complete intercooling, ya shabab, that the temperature T3 out of the intercooler is the same as the inlet temperature T1. Now we can take it and pass it actually through a second stage compression or a second compressor. Here, this is compressor number 2. Then it will be compressed and the gases will be leaving at state number 4. Okay? And this is the representation 1, 2, 3 to 4 in this case. But the compressor work in this case, shabab, will be what? Will be the compressor, the work of the compressor 1 plus the work of what? The work of the compressor 2. Is it, shabab?
Right.
طيب, I just want to make this figure a little bit bigger. So this is very important. So what we have done is multi-stage compression with intercooling. We said the minimum case, the minimum situation, when the process is isothermal, that is B1 and that is B2. If the process is isothermal, T is constant, that means the work will be minimum in this case. That is the minimum work. But we said we cannot do that. But we can do the process polytropic to an intermediate pressure Px, Pv to the power n is constant, from 1 to 2, and then from 2 to 3 at the same pressure Px, we can intercool until we reach the same temperature. This line is representing constant temperature. Then at state number 3, I will go back and have another polytropic process, Bv to the power n is constant. And this is actually the final state 4, and this is the final state 2 prime. So see, here, if I'm using multi-stage compression with intercooling, this is the final point. If I consider the isothermal case, which is a case I cannot do it, this is point number 2. If I'm considering one stage directly polytropic, then I can say actually reach the point 2 prime. This one is impossible, I cannot do it. This one can be done, but we can improve it by considering compression to intermediate stage and cool down to the initial temperature, and then we can reach actually this point. So this point actually is the best that we can do through what is called actually multi-stage compression with intercooling in this case. We cannot reach the isothermal line, but in this case, if you have, instead of following the isothermal line, I'm going polytropic, then cool down. Go polytropic and then cool down. If the pressure difference is very high, then in this case, instead of 2 stages, I can use more than 2 stages. I will go polytropic and then cool down. So, and so on. So I cannot follow this line, but I can do this. I'm just going beside this line. This is the best I can do. Polytropic, cool down. Polytropic, cool down. Then actually I'm just going close to the isothermal line, because the isothermal line will give me the minimum input work. Is it clear, Shabab?
Yes, so we go close to isothermal.
Yeah, so this is the best that we can do. Go polytropic and then cool down. This, in this case, the cooling. Go polytropic and then cool down. So I'm just trying to stick to the isothermal line, but I cannot follow the isothermal line. Okay? In this case, the compressor work will equal to, this is a polytropic from 1 to 2, polytropic from actually, in this case, this is state number 3, 3 to 4 is also polytropic. So polytropic, we have proved the relation. It will be N R T1 divided by N minus 1 multiplied by B2. B2 in this case will equal to what, Shabab? We call it the intermediate pressure, Bx. Okay, so it will B2 is Bx for the first compressor, Bx over B1 to the power N minus 1 over N. Plus the work of the second compressor, we said T3 is the same as T1 for complete intercooling. So it will be N R T1 divided by N minus 1 multiplied by the final pressure, which is B2, the final pressure, divided by the intermediate pressure Bx. So B2 over Bx to the power N minus 1 over N, and we have minus 1. Okay? How we can get, Shabab, how we can calculate the optimum value of Bx, the intermediate pressure, for the minimum compressor work? How we can make it mathematically? This is an equation. Forget about the compressor. We have an equation, something y is equal to function of x. How we can get actually the optimum value of this x in order to have this value minimum? What should we do with this equation? Mathematically, this is mathematics. So in this case, we have to differentiate. You can do that, try it, and equate the value to 0. Differentiate the reversible work with respect to the compressor work with respect to Bx, differentiate this equation and equate actually the value to 0 and solve for Bx. If you did that, you will find the optimum value of Bx is equal to the optimum value of this ratio Bx over B1 should be the same as actually the value of B2 over Bx. So that means it is just equal compression. Bx over B1 is the same as B2 over Bx. Or we can say the optimum value of Bx is equal to the square root of B1 multiplied by B2. Okay? Is that clear, Shabab? And in this case, the compressor work, which is work of compressor 1 plus work of compressor 2, now it is the same. It will be the same in same T1 is the same as T3, so we have T1, and Bx over B1 is the same as B2 over Bx. That means this term is the same as this term. So that will equal to 2 multiplied by the work of any of the compressor. Let's say 2 multiplied by the work of compressor 1. So it will equal to 2n RT1 divided by n to minus 1 multiplied by Bx over B1 to the power n minus 1 over n minus 1. Is that clear, Shabab?
Yes, clear.
This is not the minimum. The minimum is the case when we have isothermal process. But this is the best that we can do. This is the best. The best to be done for a compressor. So it is better, Shabab, if you are designing a compressor to use multi-stage compression with intercooling. Look here. Here is the case. Isentropic give us the maximum work. Polytropic give little bit reduced work. Isothermal should give us the minimum reversible work in this case, and this is the reversible work. But the equations, Shabab, are not proved. You have to look at the proof here. Then you can that we have done. You can look at revise the video again. Then you can look at the proof. And we said we cannot make it isothermal. But what we can do is that we can go as close as possible to the isothermal line considering the polytropic process. And this is the compressor work in this case. Try to translate this, Shabab, and see example. Just this example, you can just substitute here. So here in this example, air is compressed steadily in a reversible compressor. So here we have a reversible compressor. So work integration of PdV. He gives the inlet pressure, inlet temperature, and he gives us the exit pressure. And we need to determine the compressor work using isentropic process. Key is equal to 1.4. 1.4 for air, Shabab, you have to keep it in mind. Key for air is 1.4. For any other gas, you can get it from table A to B or A to A, as we said last time. And second process, so we need to calculate the compressor work for the isentropic process. For the polytropic process, N equal to 1.3. For isothermal process, and finally two-stage compression with intercooling for actually value of polytropic index equal to 1.3. So here is the relation for isentropic that we have developed. K is equal to 1.4. R for air is 2.87. Can get from table A1 if you don't remember. Temperature T should be in Kelvin divided by K minus 1. B2 over B1 to the power K minus 1 over K. We have it, we can substitute it in kilopascal. B2 over B1, then we can get this value of the work. This is the isentropic. We said the isentropic will give us the maximum input work, maximum reversible input work. Because the actual should be higher. We are talking here about reversible one. Isentropic will give us actually the maximum reversible work. But if we consider reversible but polytropic, not isentropic, then in this case, this is the equation. Just instead of K, I will replace it by N. Then substitute N is equal to 1.3. Substitute, this is the value of the work. Compare this value with this value. So in case of polytropic, Shabab, because the system is allowed to exchange heat, release some heat, then in this case, the work, which is the area under the curve on the VB diagram, should be less than the case of what? The case of isentropic. In case of polytropic, it is 246. In case of isentropic, it is equal to 263. Okay, so the polytropic process can reduce the input work to the compressor. And if I consider it isothermal, it will equal to RT ln B2 over B1. We have developed this equation. Just substitute the input work يا شباب here for a reversible isothermal is the minimum in this case. So the minimum input work to the compressor is equal to 189 for the isothermal. And this is actually the input work represented by this line, the isothermal line. Compared to those values, it is 189, so it is much less than the case of isentropic or polytropic. But we said we cannot make it isothermal. What we can do is two-stage compression with intercooling. And in this case, this is the relationship. So it will equal to 2nRT, 1 divided by n minus 1, multiplied by dx over b1 to the power n minus 1 over n minus 1. And we said the optimum value of the intermediate pressure, Vx, is the square root of b1, is the square root of b1 divided by b2. Then I can calculate Bx, it will equal to 300, just substitute in this equation here. Then in this case, we can calculate this work. This work, يا شباب, should be what? Should be higher than the isothermal, because we cannot do it. But it should be actually less than the other two cases when we have polytropic from the inlet to the outlet, and also when we have isentropic. Is that clear, يا شباب?